So I've split the talk up into 3 bits. The first bit is going to be the basics. I'm hoping we can basically skip through this and hope that people understand this already. We'll see how fast we can go, but this is the stuff that we're assuming for the rest of the presentation. So if I'm going a bit too fast in this bit, slow me down, because if you don't, you'll miss the rest. Then we're going to be talking about designing a binary file format. So we'll be talking about what kind of stuff you need to put in a binary file format, what kind of things to think about when making it. And then we'll be going back to reverse engineering. My personal favorite, but it's not practically as useful as the other bits are. So let's do the basics. What can you actually do in a single bit? A single bit is more limiting than you think it is. It's literally, it's there or it's not there. You can use it for a sign bit, the number is positive or negative, and you'll have to pick for 0, because you can't make 0 not negative and not positive. There's no space for anything between. So you can also use it for something that's a binary option. You are either a vegetarian and are limited to that, or you're not. At least I thought it was. And you can use it for graphics, because pixels can be on and off, and if you have enough of things on and off, you can make patterns and make things look like something. So that's 1 bit. How much can you do with 2 bits? Well, 2 bits is enough to have a bit more options. You can have a yes and a no, or somebody didn't fill in the question. You can have going left, going right, going straight ahead, or doing something else. But there's no space to say what actually you're supposed to do, because that's the 4th option. We're out of bit. You can use it for graphics. High resolution, Tandy graphics. If you still remember these colors, this is what you get when you have 2 bits of data. You have black and white, you have cyan and pink, and that's all the colors we have. It looks better here than it's supposed to, because somebody is clever enough to use the colors in a dithering pattern, which makes it look like there's more colors than there actually are. And you can also use it for when you're in India. And the option is not just being veg only, you also have the non-veg only option. Given that option, I'm tempted to cross both and see what they do. So in 4 bits, what can you do in 4 bits? You can have a small enumeration, you can have a couple of options. And you can have a useful palette. This is the first time that we actually have like a bunch of colors. We can make something that looks nice. And while I've tried, this is the C64 Palette. I've tried to make games with this, and I absolutely cannot. I'm just not graphically able. But some people can make things like these. And this is just 16 colors. It looks bloody awesome. And if you look up close, you recognize the exact colors that they used. But just looking from a distance, it looked like it's a whole lot more than it actually is. So going to 8 bits. 8 bits is enough to do primary school math. You can add numbers, you can subtract them, you can get some negative numbers. You can have a useful general palette. This is the web-safe palette, which is the thing that was used on the internet before we had enough memory to store actual graphics. You can have a full grayscale palette with basically no interruptions. So you can take grayscale pictures. It's starting to get useful. We already had 3 steps. Let's go to 16 bits. In 16 bits, I can have all colors. Almost all colors. Because if you look closely, you can see some banding between the colors. It's not actually a continuous one yet. We can step it up 1 more and go to 32 bits and be what is basically photorealistic. We have enough bits per pixel to represent any color. And if you like the picture, you can buy it online. If we go a bit beyond that, we run into a different problem, because human eyes aren't that good, but our camera is. So we can take more realistic pictures than our eyes are able to see. But with a tone mapping operation, we can take the data, and instead of just having a flat mapping, we can extract more dynamic range from it than it actually has, and get to the pictures like on the right, where the dark bits have detail, and the light bits still have detail, and are not just washed out white. And going back 1, if we have 32 bits, we have enough of a number range to almost identify everybody on the planet. Almost. Every 2 people will have to share a number. If we're in 64-bit, we can give everybody 1 billion numbers and still have left over. So we're getting quite big. If we go to 128 bits, We can just hash any data for practically any data set and get no collisions. There's so much space. It's practically impossible to get a collision. And somebody took that idea and made it into a UUID, a universally unique ID, which isn't actually unique, but it's close enough. You could also look at the entire universe and find all the things that are planets, and then find, assuming that every planet has something like humans on it and like 8 billion of them, and give everybody on every planet in the entire universe their own identifier. Because we have a lot of numbers now. It's a lot of space. We can identify every 2 micrometer cube in the entire Earth. We have that many numbers. That's a lot of numbers. But actually, what can we do with these numbers? So how much would it actually take to store data? Well, there's a theory about how much data or how many bits you actually need to store something. And it's called Shannon entropy, named after Claude Shannon, a researcher from the 50s. And he calculated that English text, for example, on average has 2.6 bits per character of actual entropy. Which means that you will use more to properly store it, usually. But if you're trying to make it as small as possible, there's no real way to get below 2.6, because actual text has about 2.6 bits of information per character. If you have numbers, there's a mathematical formula you can use to find out how big your number space needs to be to store whatever kind of number you like. But we can still cheat this. We can beat this. So what if I told you that we can store the entire matrix in a single bit? Anybody believe that? It's true. No? We can store the entire movie, The Matrix, in 4K in a single bit. My custom file format has 1 bit, and if it's a 0, it's the matrix. If it's a 1, it's something else, and then the entire file is appended, because we still need the entire file. It's kind of cheating. But it also has a downside, because now my compressor is 14 gigabytes, because it's basically detecting a bit, and then if it's 1, then I'm just copying it. If it's 0, then I take the entire matrix I have in my compressor and just output that. Okay, so cheating works, but it doesn't work general purpose. It's not a practical thing to do. So there is a limit to how far we can go. So how far can we go without cheating? If it's actual random data, there is literally nothing you can do. There's a proof you can make that says that given a total number of inputs, your output will have to have the same number of possible outputs. And with the formula we had for numbers, we can prove that it will take at least the exact same number of bits to encode that. But we can shift it around. We can make things that are likely be more compressible, and things that are unlikely, like random-looking things, be less small. So the base idea is that we have a bit of data, and based on that, we predict what's going to come next. And if it's not that, then we'll write down what it actually was. So let's see if this works. I'm going to need a bit of audience interaction. So we have a bunch of starts. Fourscore and 7 years ago. I have a dream. Once upon a time, comment, game over. And supercali, you're awesome. Now that's a good compression. Fun fact, I had this as my Wi-Fi password at some point. Everybody hated that. So what we're actually going to be doing is trying to put information in bytes and in bits. We're going to be trying to compress as much as we can into a fixed size amount of units. Encoding things into bytes is a lot easier. We have a standard split up. It's a useful size because we can fit 256 things into it. And we don't have to use bits to encode how many bits we have available. It's a nice assumption. But if you do things in bitpacked, it will be more compact in nearly every case. So in many cases, it's mixed. We have a couple of fields that are like 5 bits and 3 bits. We first pack that into a byte, and then we pack the bytes where we can. So for the rest of the talk, I will need everybody to be able to read hex and understand binary. And I'm assuming that people can do this. If I show this table, does this make sense? If it doesn't make sense, please raise your hand. Okay, we're good. That's awesome. And we're going faster. So how much can we actually do with 8 bits? We can use it as an index into a single lookup table with up to 256 entries. We can use it for variable number encodings, where we take half the space for a small number and the 1 bit at the front to say it's a longer number. We can use it for run length encoding and back references. So let's look at the actual bits. For run length encoding or variable length encoding, a 1. That's easy. It's a 1. We change this to a 2, it just becomes a 2. And if the top bit is not set, nothing happens. It just is the 2 that we think it is. And this works up to 127. And after 127, we need to set the top bit because we don't have space anymore in the part that we allow for that. So we will set the top bit, and that actually pushes in a second byte. And decoding this takes a bit more effort. So every time the top bit is set, we pull in 1 extra byte until we have a sequence. And from that point on, we start our decoding process. So we take these values, written down as bits in the bottom. We swap the order. So the one with the 1 byte is on the left, the 80 byte is on the right. We drop the top bit. The top bit is marked in red, and we just remove it. And this is basically the decoding we have. Now, to make this more readable, we'd like to space it like a normal hex dump number or a normal binary number every 4 bits. And writing this out as hexadecimal gets us hex 80, which is 128. And this scheme works for nearly every number. So we can take 69,420, do the same thing. We take the bytes, written as binary, flip them around in order, drop the top bit, respace, and we get 69,420. So we can encode every number in this format. And despite knowing this number doesn't fit in 16 bits, so we'd have to use 32 bits, we're actually only using 24. So this is more compact. But when can you actually use this? What kind of data is this good for? Well, real-world data, like house numbers. So I looked it up. The biggest house number on the planet is almost 1 million. It's a really big house number. There's a structure to it, but ignoring the house number structure for a bit, if we're trying to store this as a 32-bit integer, we need to store every house number as a 32-bit integer. But other than the US, most people live on house numbers like 2 or 12. And even in the US, they live on 100 or 301. And those numbers could be stored so much more compactly than a 32-bit integer. So if we use the full encoding, we'll use 4 bytes for each house number. If we use a more clever one, we can store every number in 3 bytes or less, and practically all numbers in 1 or maybe 2 bytes. Now, if you're thinking about actually storing house numbers as numbers, don't do that. There are crazy house numbers in the world. You cannot possibly store them as anything other than a string. Okay, the second one, we have run length encoding. We start by having a bit more complicated first byte. Our first byte is now telling us what we are actually doing. Are we copying the next sequence or are we repeating the next byte? And then we have a number indicating how many times we do so. So reading this number, we have a 1 bit which says that we're repeating. If it's a 0, we're copying. If it's a 1, we're repeating. The number before that, decoded, is a 9. And we're encoding a 9 to indicate 10, because otherwise we'd have a value to encode 0 repetitions, which is wasteful. So we move that by 1 so that it's more useful. And in this way, we can indicate we have 10 repetitions of a byte of 10. And now we've encoded 10 bytes of data in 2 bytes. But let's again look at some actual data and see how much we actually get with that. So we have a sequence of data. And to run length encode, the first thing we do is find a stretch of values. We find a stretch of value that is the same. So all the way at the top, we have values 9e. Below that, we have a lot of values be. So these are the runs that we identify, and the bit in between, it's probably a gradient, I guess. but it doesn't compact well with this approach. But let's see what we can do with these. First thing we do is we have 9e. We have 5 copies of it. So we encode that with a 1 at the end, 4 before that, ending up with the hex value 9. We have 09, 9e. This is 5 bytes. Then we copy 3 bytes. So we have a single byte saying we want to copy 2, because we have 1 extra. And then we copy the next 3 bytes. The next 3 bytes are just plain copied. So we sort of compressed 3 bytes into 4. So in that place, we're losing a little bit. But the next bit, we're gaining again, because we have BE, and we have 24 copies of it. And we can do that in 2 bytes. So taking out all the commentary and putting it all back together, we get to a sequence of just 8 bytes for something that used to take 32. So we've gained some more space. But these are nice synthetic examples. So let's go for a range of address numbers, say a street. And these are the house numbers that I have on the street. We start with 1, 3, 5, 7, 9, all the odd numbers. And for some reason, there's a hole between 23 and 31. Somebody probably planned a couple of houses, but somebody built a street instead. It happens. So if we pack this as 32-bit integers, which we initially assumed, we'd have 64 bytes. If we put this in Protobuf, just as is, we have 16 bytes. But looking at the data, I can see there's a repetition. Every time, except for a couple of times, we're going up by 2. 2 more, 2 more, 2 more, up until 23. So if we take the difference, we get a sequence that looks like this. And that looks like an ideal candidate for running encoding. It's a data-specific transformation. We know something about house numbers that allows us to do this. House numbers are increasing, and they have a fixed offset between them. So knowing this, we can change the data with a transformation to make this available to whatever compression format we have. And after this point, we can run length encode this. So we have 1 copy of a 1, 11 copies of a 2, 1 8, and 3 2s. And each of these encodes as a single byte. So the total of this, again, run length encoding, putting it in the Protobuf, would be 8 bytes. So we can store more data. The last one we're looking at in detail is back references. Again, we have a bit of a representative bit of data. This is a color gradient. And if you look at it, you can see some repetition. It's not the repetition that's easy to compress, but it's the kind of repetition that is basically repeating stuff that we had before. Because the second line is like the first line. They're almost the same, except the first one starts with a 0 and the second one ends with a 6. But if you could encode somehow that, you know, instead of just outputting bytes, just take whatever's back there and copy it in here, that would result in a pretty good compression. And it's not just that line, it's the next one. And we can go down the entire image, find 5 instances of this. So writing it down, we basically have copy the 6 bytes that we start with, and then repeat that bit that we just had, the last 5 bytes, and add 1 more. Repeat the last bit, add 1 more. Repeat the last bit, add 1 more. And looking at this text, this feels big. It feels like it's more data than we just had before. So it doesn't look like it's actually saving us any data. But let's compress it in bytes and see how much it actually saves, how much it actually gets us. So starting from the start, we have a 0A indicating we're copying 6 bytes. We have the 6 bytes. And then we have an indication saying we would like to copy the 5 bytes we just had. So back 5, we would like to copy those 5 bytes. And we do that in a bit pack format. We have a single bit indicating that we're doing this kind of operation, as opposed to 0A ending in a 0 bit. We have a 4 indicating that we are going back 5 bytes, again, with the 1 off. And we have another 4 indicating that we'd like to copy 5 bytes. Which means that we're basically saying in a single byte to copy 5 bytes. And then the next one is an indication that we just want to store 1 more byte. Do the same thing, store 1 more byte. Do the same thing, store 1 more byte. And putting this back into the format we just had, making it look similar, we actually see it's 14 bytes shorter. So this is the kind of compression that works. This is basically gzip. If you ever thought gzip was magic, sorry, it's no longer. And let's look at Protobuf. Protobuf is one of the formats that's used a lot, and it is actually remarkably compact for what it does. It's one of the easier ways to make a binary format without doing all the stuff by hand. And for Protobuf, we're picking up the pace a little bit. We basically have an encoding for a struct. Protobuf has structs. You can have structs in structs. You can have strings. You can have ints. You can have all the real-world kind of data that you'd have. And every struct is basically just a serialization of everything in the struct. So let's take the example from the website. We have a person. The person has a name. It's a string. It has an ID. It's an int. He has an email. That's a string. And encoding this gets us this. So every time I look at a new kind of binary format, I'm like, what am I even trying to see? What should I be looking for? Splitting it up according to what's actually here gets me this. So we have a couple of indications. We have the yellow bits, and I recognize those. Top one is my name, the bottom one is my email address. The middle part, that's the number 42. The rest of the numbers I don't quite recognize yet. But I do see that my name, which is 5 characters, is prefixed by the number 5. My email address, which is 17 characters, is prefixed by the number 17 in hex. So then we have 1 byte at the front of everything saying what it is, I'm assuming. And looking at how Protobuf actually does this, we have the prefix telling us which field it is, field 1, field 2, and field 3. We have an encoding which says if it's a length prefix one or if it's a variable length integer. And then we have the data. So that's a very compact way to encode my data. Hey, so this was the basics. Now, let's get into designing a binary file format. And the number one question is, why are you doing binary? This was a question we had a lot in the past. And there are basically 2 reasons why binary is bad. Binary has an endianness. If you're reading a number, you don't know which order to interpret the bytes as. And that used to be a bigger problem, but it's a very easy one to handle with a library. Get your library to give you a big endian or a little endian number, and you don't need to care anymore. The second problem that we had, which was way bigger in the 90s, is new line conversion. There are a couple of setups, especially particular server and client combinations, that assume everything is text. And that led to the problem, and it was so widespread, where people would have corrupted executables, corrupted zip files, corrupted MP3s, corrupted everything. And it happened so often that somebody made a tool to take your corrupted data and uncorrupt it in place. And the tool that actually caused the corruption back then usually was Internet Explorer. Which means that the problem has disappeared because Internet Explorer is gone. So that's practically not an issue. The first one we have solved. So we don't really have any reason not to use binary formats. And they're more compact than text formats. What kind of binary files do we have? In general, there are 6 general types of file formats. The first one is a flat file. It starts with the data, and it has every bit in sequence. There's no structure to it, there's no headers, there's no information telling you what you're reading. It's just bytes. And we use this for raw images. We use it for lookup tables, like a sign table. And we do use it for palettes. Not necessarily because it's a good idea, but because somebody started, and I guess that's the format we have. It also means you can't put 2 palettes in the same file because nobody would know what you're meaning. The second type we have is a header with flat data. And this is a major improvement. It means that when you're opening a file, your tool can say this is the wrong kind of file. You're trying to open an image as audio. You're trying to open audio with MS Paint. It doesn't work that way. It also means that if you know how big the header is, because the rest of the data is still flat, you can still read it, and you can easily write it as well. You can just take your data, append a header, and put the right data in to make it interpretable, and that will make it work as a writer. It means that these file formats are very easy to make a simple writer for. The third type we have is a header with an index and multiple bits of data. And this is the thing that was used a lot in the 90s. the early 2000s, 2010s, when making computer games. Computer games tend to have lots of things. They have audio samples, they have images, they have 3D models, they have textures, they have so many tiny bits of data to keep around. And putting 10,000 or 100,000 files on your file system, when your file system can't handle more than 30,000, would break every client's computer if you didn't compact it somehow. So what they did is invent a format that basically works like an archive. It's a header, it's saying this is an archive file, there's so many entries. Then there's a giant list of all the things that are in there. At this offset, we find that much data. At this offset, we find that much data. And some of them have names, some of them have hashes, some of them have nothing. You just have an index. And this basically takes all those files and binds them into one block. And the block then allows you to distribute your game. People can't easily read it, can't replace things. There's a lot of reasons why game developers like this. In some cases, this is also used for file formats with basic animations. If you took a bitmap, and instead of having a single block of data, you had a couple of them, maybe with an X and Y offset, you could basically do animation with bitmaps. And you'd have an index next to your header saying how many you have. But this is still a basic kind of file format. We're still just storing a single type of data. But if the type of data we're trying to store is a bit more complicated, like 3D objects. 3D objects have vertices, they have normals, they have texture coordinates, they have entirely different things, like the actual textures you're trying to use. They have bones, they have rigs, they have animation data. And all of that ties together into one model. So we're trying to store disjointed things into a single file. And to do that, we basically took the thing that we had before. We have a header with some data, and we transformed that into having a sequence of those things, where each of those bits can have repeated sequences inside it. So we have something called the model, and the model has vertices, and it has normals, and it has texture coordinates. We have a rig. The rig has a bone, or a set of bones, and it has a number of animations. So these kinds of things are used for that a lot. It's also used when you're watching movies, because movies aren't just images since the 1910s. We have images and audio. So we have two things that we'd like to keep together, but then sort of interleave, so it's useful. So all of those formats tend to be chunked files as well. And up to a point, XML is as well, except XML is not a binary format. So it's between parentheses. The fifth kind we're looking at is a record sequence. And records are the ancient idea of storing data. It's basically a header with data, followed by a header with data, followed by a header with data. It works really well if you have a tape, because that's just how the tape is going to send it to you. And it works well if you have relatively custom structured files like Protobuf, because you don't necessarily know how things should be grouped, but you do know there will be a sequence of things. So these formats do this. And then we have a legacy of the 90s, which is a pseudo file system. In some cases, especially the Windows dark files, they went to the trouble of making a file into a file system in itself, including allocation tables, indirection tables, a FAT table saying where all the blocks are reoriented, so that when you're updating your document on a floppy disk, it would be faster. And these things are great if you're doing a PowerShell update on a really slow medium. Thing is, we don't have slow mediums anymore, and nearly every file fits in memory. So the thing we do now is just take the file, load it in memory, re-encode the whole thing, and store it back. And that brings us to the downside of this one. It's very complex, it's very bug-prone, and this is a format we really should never be using again. Last time I've seen somebody make this is in the early 2000s. And then we have the last one kind of limping in, which is, I made my own custom file format, but it's just a zip. And this is one that happens a lot with file formats that are essentially text-based. So if you have a document in docx, it's a zip file with XML files in it. If you have an open document file, it's a zip file with XML files in it. If you have a jar, it's a zip file with class files in it. If you have an APK, it's pretty much the same thing. And all of these things basically start by having a zip because it's easy and you don't need to write tools. And then they add their own custom extensions. For example, APK has a signing mechanism, so you can make a signed zip file, which any tool can still unzip, but making one will require your custom tooling. Since this is basically a cheat, we're not going to go far into detail on this. It's a useful thing to know that it exists and that many people do. So then, if we have a binary file, how do we use this? I mean, we can make a document file, we can make a video file, but the file format we're making should be suitable for what we're trying to do. And there's a couple of ways of using a binary file. The first one is to stream it in. Streaming in and streaming out has a really good benefit. It's a very low memory use. You can make a small terminal with, say, 8 megabytes of memory and have it display 4K video. It uses very little data. And it's excellent if the data you have is continually updating. It's the ideal format for stuff that is real-time streaming in. The second kind of file format that we have is a memory mapped one. And this is the one that I particularly would like to go into details on. Memory mapped files are those that you can load in very quickly, that can contain a lot of data. And when I say a lot of data, I mean it's good for large files, as in almost the size of your memory. With random access, you can just access any bit of it. You have a quick loading time, and there's no loading overhead. There's not a lot of code involved. And it's great for huge files, by which I mean they're too big to keep in memory, but you can store them on disk. Because the stuff that you're using often will be paged in, everything else will be paged out. And your access times will be good for the stuff that you're typically accessing, but you don't have any kind of code to handle paging in, paging out, finding out what's used often. Your operating system does it for you. And it can be really fast to load, if and only if you've made it fast to load. And the star is because to load something fast, you need to not actually look at the file. The more you need to look at the file, the more you need to load in, the slower everything gets. The best thing you can do in a memory map file is have an index, have headers that describe what's in there, have an index that says what to find where, so that if you're trying to read something, you can just do so without reading through the whole file. If we take a stream of video and we're trying to seek to about the middle, it's practically impossible to do so without starting at the front and just skipping ahead until we get there. If we have an index, we can go to the index, find the right point, jump right there. Almost instant. And this has a lot of real-world analogies. We have a first letter tab on the side of a phone book, which says if you're looking for the letter Z or the letter T, you can go to this bit, and this will be all the T's. It's like an index at the end of a book. And in many cases, these indexes are like the thing you would have on a DVD. You have an overview that shows you have these bits of movie, and you can skip to the right chapter. That is literally the index. And it has a byte offset where that chapter starts. And then we have any other kind of file. Anything that you cannot stream, you cannot memory map. I call it a loadable file because you can still use them, but they're basically the slowest kind of thing. You take the entire file, you parse through the entire thing, convert everything to memory structures, have a giant pile of allocations, have a lot of data in loading. You take a long time to open the file. But these have a different kind of use. If you have a small bit of data, the loading time isn't actually that hard. The amount of memory isn't actually that big. So for an image, this is fine. If you have a sequence of images, you could store every image as a loadable file inside a memory mapped file that has an index. And that brings us basically to a hybrid. Having a file that has a memory mapped structure, we have offsets, we have indexes, we know where everything is, but the kind of stuff that you would use together is stored together and as compactly as possible. And if you have very localized access, like in a movie, you're watching that frame with that audio. You're not watching on any of the other frames, so you're very localized in your access pattern. Or inversely, if it's a very long tail style of access. For example, if I have a navigation system for cars sold in the UK, you're very likely to load the map for the UK. But maybe you took the ferry and you drove to Dubai. So I need to have all the data available for the entire world, except I know that I will almost always just use the UK. So for these kinds of things, this is a great format. So designing a binary file format, we start with step one. Step one is, what am I going to do with it? How am I going to use the data? We're not even starting about what actual data it needs to be in there, we're starting about what you're doing. If you have an algorithm that uses a lot of data, it will often be bounded by the speed at which you can load your data. And the data that you have in memory is something you refer to as a working set. And we want to make the working set to be as small as possible and as efficient to get out of your file as you can. And to get a bit of a mental understanding of what a working set is, I've found an analogy. So basically, this is all the data we have. It has a lot of bits, has a lot of stuff, and there's a couple of things in here that we need. But trying to get it from this entire working set by sifting through it and trying to find something is slow. The best thing we can do is put everything in its own chunk. And there's a company that does it for us. So we have 4 chunks that we can load at the time that we need them. We can do those in time. So these are basically like the pages and the bits of the file that we're loading at a time. And then from this chunk, we're going to load the bits into level 1 cache that we need for every step. So the top left here is your level 1 cache when trying to build something from Lego. And as soon as you've used that bit, you take your intermediate product and go to the next bit of level 1 cache to be loaded, load the next cache line, and do the next operation. Worked great. The thing to realize is that as much as we like to have this giant pile, it is extremely inefficient. And our computers are no different from us. As much as we have trouble seeking through this, they have trouble seeking through the entire data bundle that you have. So the thing we're trying to do is use as much of our cache in a more efficient way. Instead of having everything, we want to just have the things that are relevant, the things that are correct. If we put those in cache, our cache is much more efficient, and we can build things much faster. And caching isn't just a thing that's called cache. There's a level 2 cache, there's a level 3 cache. The bigger your files get, the more levels of cache you implicitly have. My main memory is a cache for a file of terabytes. My computer, my whole computer, is a cache for a file of multiple terabytes. And I will cache part of it. So that's step 1. We have, for example, a difference in video file formats. On one hand, video file formats store a video with audio. You'd argue that it's basically one file format, just make one thing. But the use cases for viewing and editing are so different that if you're viewing, you want it to be in sequence. If you're editing, you want it to be available, but you mostly want these to have small snapshots, so you see what kind of stuff you're editing into what place, without reading the whole video file every time. After we know what we're going to do with the file, we need to data model the stuff that goes in. We need to know what kind of stuff we're using. We have data, we need to know how they relate to each other, how many things of everything we have, and a bit of an estimate of how big things are, how many things we need. So how much of something do we have? Is there a useful group? Is there stuff that we need to bundle together? And given the kind of stuff that we're trying to do, is there something we need to duplicate in a different kind of way? Is there some kind of index we need to make? As soon as we have this, we start by trying to map things into the stuff that's in the file. So we take the bits at the bottom, like the address, your house number, the people in the street, and we try to put those into a group. And from the other way around, we take the things that we have as a global thing, so we take the root network and the searching index, and we index those things top down. We index all the places you would like to go to. So we try to group things into a single cache line if we're using it as one. We're trying to separate things if we don't use it as one. And for example, the index for trying to find out who lives in a street will be a different one from the one that you use to drive on that same street. It's the same street, but there's 2 different use cases, and we'll probably have 2 different files or 2 different bits of our file. And as always, indexes are great. If you are not even looking at data, there is no way to be faster than not looking at all. After this step, we start by making a specific kind of file format. We pick some kind of format that we can use, some kind of libraries that abstract this for us. And in some cases, these libraries will have generic support for everything, but there are faster things, like arrays. If you have specialized data structures, there are good reasons to use a completely custom format. If you have B+ trees, radix trees, arc trees, quad trees, indexing, that kind of stuff doesn't work well with a generic library. And using some kind of custom format is definitely the way to go. The thing that we do in every file is try to start with a magic value and a version number. The reason why we do this is so that if you have the wrong file, think back to loading audio files in your graphics editor and graphics in your audio, we want to error out quickly. If you have the wrong kind of tool, we want to say, nope, that's not going to work. This file is too new, this file is too old, you're trying to navigate on an image. There's a choice between big endian and little endian. If you're using a memory map file, there's an option of just mapping a struct onto it. Yes, it works, it will be quick, and it will be endian dependent, which means that it will work until you have a different kind of CPU where it just completely doesn't work at all and it will break in horrible ways. Given the libraries we have now, the much better option is instead of trying to do this, to not even try, but to make a type that works like a view. It's like the struct, except it does an explicit way of accessing the data and it deserializes it for you in whatever way you need. This will practically always be better. The next step is to provide access. Load the file in memory. There's an option of map lock and map populate, which tries to load the entire file into memory and then lock it there, which is good if you want to have guaranteed performance. And you can explicitly choose not to do these so that your startup time will be better. It's a bit of a balance. And then we load from the file enough to know that the file is valid, that it's the version we support, that we have the indexes loaded, and that's the point where we stop. And then we take a view style access to whatever's in there. We know what's in there, we know where it is, we know how it's encoded, but we're not looking at it until we need to. And as soon as we have this, we can start using it. As soon as you start using it, you find out that actually you're wrong. See also Bjorn Fowler's talk, you will be wrong. So the next step is always to iterate your design. Take the stuff that you did, find out how well it does in practice. Try it out, try a couple of different options. Check on your target hardware. Maybe you have a really slow kind of disk and putting things in more compactly is faster because decompressing is faster than loading. Or maybe it's the exact opposite. And you have a NAND SSD that is 4 gigabytes per second and it can load your data so much faster than your CPU can decompress. And as soon as you have this, you run into the problem that now you've got multiple versions. So how do you deal with multiple versions? Well, the first approach is instead of having a single file format with a reader to just copy the whole thing over and make it 2 copies, and then update the second one to be the new file format, the old one is the old one. It works, but you will have a lot of duplicate, and if there's ever a bug fix, you will forget to update half of them. So it's not great. The second option is to take the one that you had and just add a couple of if statements, and a couple more, and then a couple more. And you turn out with spaghetti. So both of these options, they're not actually great. A better idea is to use something that's backward compatible. Trying to make your file format such that if you're adding things to it, it will still work with the old loader, means that you can add the option to load more things, and it will work with the old version, but you can still always load the new files with the old one. This means that your code is a lot more compact, but you will have to think a lot more about how you're modifying your file. And this is what pretty much all common formats do. And there's one more trick that people try to do now, which is backward and forward compatible, which is like Protobuf. Here, you have a couple of fields that are serialized. You can add fields, and those will be serialized along. And if you're reading it and you don't know a field, you just skip it. In theory, that does perfect versioning. In practice, it doesn't work at all. Because you have data, you have loaded half the data. Did you need that half you didn't load? Or in case you use an old file, maybe something is missing. And now you're pretending like the data is there. There's a lot still to be done. There's even a more complicated version which takes this idea and makes it into a self-describing file. These have a serialized version of their own schema inside them as part of the data. And that sounds like an excellent idea, because now your file is wholly self-describing. It has all the information about what information is in there. You can do everything generically, but practically it's more of a party trick. I can take the file, look at the version, and if I have a reader for that version, it doesn't do anything. If I don't have a reader for that version, it still does nothing, because I don't really know what to do with the data I'm getting. So practically, versioning is a thing you need to spend some time on. And when making a file format, the biggest problem is always this one. There are three things you get. You can make it compact, but slow. You can make it fast, but big. Or you can make it cheap, and neither fast nor compact. And for everything you're trying to make, there is a balance between the three of these. You'll need to find your own point on the balance where you want to be. For things that are widely distributed and used a lot, you will probably be on the bottom side. For things that you're hacking together, just stay on the top. There's no point in trying to make it fast and efficient if you're just using it once. Okay, so we have 14 minutes left for the last 50 slides. 55. So let's put on a turbo. We're going to reverse engineer something. Why do we reverse engineer things? Well, in many cases, things were created by somebody who didn't think about what it was going to be used for later. Like, somebody just made a thing and put it out in the world. And it's a nice data set. It was used a couple of years ago. Nobody's used it since, which means that we basically have stuff that used to be there, stuff that we'd like to use still, but we're unable to access. And a lot of that stuff is now abandonware. There's data that we'd like to use. We'd like to have this data. And the worst offender of this is computer games. Computer games from the 90s, 2000s, 2010s don't run anymore on your current computer. The executables, you could try to patch them up and get them to run in DOSBox. You could write a custom DOSBox to make it work. Or you could try to read the files into a new engine and then run the game. So for the example, we're using this game. Who's heard of it? Well, that's a total of 2. That's 2 more than I expected. So it looks like this. It's an isometric game. It's from 1995 or 96. And we're going to try to see what we can get out of this. Step 0. If you're thinking about doing such a thing, see if somebody else already did. Because you can Google and save yourself a month of work. But that's boring. So you're just going to do it again. But practically, Crusade and No Remorse, somebody already did this. It's implemented in Scrum VM since about half a year. And it is very much related to Ultima 8, which is the game before it. And I've used both of these parts as part of this reverse engineering, mostly from Ultima 8 because it's well documented. But practically, don't do that. Practically, the games differ enough that everything is just ever so slightly wrong about the documentation and nothing matches. Next step, we try to look at what the files are. So the best thing to do is to use a tool called file, which says what it is. Awesome. We've got 4 bitmaps. And all of them are just a bitmap. We can show those. I did notice that the help 3 bitmap is different from the other 2. It's surprising. You'd think that if you're writing help, you do all the help bits at once. So this is the credits one. It's the background for credits. This is the first 2 help files. Yep, looks like help. And this is the 3rd help file. This is the 90s. People put Easter eggs in games. So this is one of the creators of the game putting in a very, very odd pose. So the rest of the files, what else does file tell us? We have one file which is a DIY raw thermoscan data from a sensor with a huge slope. I think that's wrong. So I think it just saw something and assumed it was right, but this is just crap. And the rest of the files, well, it's data. Totally data. So this doesn't help. Next thing we can do is look at the files. What are they called? What could it possibly be? Well, there's a game pattern, .pal. That's a palette, I'm guessing. We have shapes. Shapes is a name in the 90s to indicate an image. I'm guessing these are images. It's a huge file. It's 40 megabytes. Huge in 90s terms. We have type info. It's info about types. We have trigonometry. We have combat information and damage tables. I guess. We have use code. Use code? I'm guessing that's code, but it's code in a data file. It's weird. We have globs. I'm guessing these are globs. We have gumps. Gumps. And there's fixed stuff. And then there's, well, stuff. Okay, this is not helpful. Maybe we can use strings to look through the file, see what they have. And we find that use code actually has all the text from the game, all the interactive bits. So I'm guessing that this is some kind of executable code scripting in the entire game. It's not x86, but it does look like it. And there's documentation on it. We're not going into details. And we have credits, which has the endgame credits. Makes sense. Then we try to identify file structures. We start by trying to see if we can find a header size, if we can find any index, if we have fixed size records, and if we have some size prefix records. These are the most common things that we find. The original software has to be able to read stuff, so it has to be somewhere, but we don't necessarily know where it is. So let's start. What do you see? Any ideas? I'm seeing a lot of bytes with 1A. I have no idea what that means. Yeah, get that. I'm seeing a lot of other bytes. And these look like values. These look like a 32-bit value doing something. I'm seeing a bit of a pattern. These look like an 8-byte struct. And then another one, and another one, and another one. How far down would that go? Well, it goes all the way down to line 6080. That's 6,000 hex bytes with basically the same kind of stuff. And then it changes to something else. Now, doing a bit of math, I have 8-byte structs, and I'm at an offset of 80 for the first one, so the total data is 6,000 hex, divided by 8 is C00, 3,072 things. I saw that number. I saw it all the way at the top. In little endian, this is C00. That's the exact same number. This number says how many entries there are. So what happens with the actual entries? Maybe it's an offset and a size. So let's look at the last one and see if that helps. It's 40A80 plus 26 is 40AB4. And if we're right, that's the end of the file. And we're right. Hey, so we found a thing. We call this an FLX file. It's an archive file. And we can decode these. But actually, we had a whole bunch of FLX files and we had DAT files. And if we look at the first line of them, there are 4 DAT files that are also in FLX format. So you can read a whole lot of files now. That's awesome. We do that, we write a tool to extract this, and then we have, at that point, like 10,000 files, which are still compacted and stuffed in there. So let's go to the next file. That's this one. Any ideas what we're seeing? Well, it's looking at the numbers, it's also looking way back. And I'm seeing lines. If I'm looking here, I see this diagonal line. I'm seeing a line here. That tends to point to some kind of fixed size data structure. How big would that be? Well, I've highlighted the 84s, and I see that there's 2 of them per line, and they shift by 2 bytes. So I'm guessing it's 9 bytes. Let's take the entire file and dump it with 9 bytes per line. And that looks like a lookup table. So we found a table of something. This is type info. We apparently have 9 bytes each. It's 18,432 bytes. So that's 2,048 times 9. We have something about types 2,048 times. And the shape file also has 2,048 entries. So we basically found the information describing how shapes are actually formatted in 3D world. The next bit, let's look at fixed. So this is the fixed.dat file, the first entry, and we have, I'm guessing, no header. It looks like there's no header. It looks like we have 1 entry per line, so this basically fixed data. It's kind of 16 bytes per entry. The next step is to try to figure out what we're seeing. So we're guessing a field, and we check the field with all the values we can find to see if there's something that tells us that we're wrong. And we just keep trying this until we find enough data or until we stop trying. And that gets us to this point. We have 2 fields at the start, which are 16-bit fields, signed or unsigned, I have no idea. And we'll call these X and Y. I think they're coordinates, there's wild variation, and there's basically a good spread of numbers in every file. The third one, no idea. But given that it's a 3D-ish game, I'm guessing it's a Z-axis. And then we have a 2-byte entry that tells us what type it is. And if check this, all of these numbers are within the range of shapes. In fact, they're all lower than 1400. Except that nearly all of them are 10 hex. And I tried looking at 10, and it doesn't seem like anything useful. So let's take all the 10 entries and see what else we find. And we see that in this column, there's a lot of variation. So remember the globs that we had? Not the gums, but the globs. Turns out the globs are a kind of compression. So each of these entries actually refers to a bunch of things. So looking at globs, we get these bits. Going a bit quickly through the reverse engineering, we have something that's a 26-byte file starting with a 4. We have a 62-byte file starting with a 10, and a 38-byte file starting with a 6. Now that looks remarkably like how many things are in there. And if you do a bit of math, it's correct. The file size is however many numbered that says, times 6 plus 2. So the 2 is a header of how many things are there. You could have omitted that, but I guess you didn't. And we have 6-byte entries. So what's in the entry? Well, that looked like a rectangle. Looking at the first two as an X and a Y, that might be a rectangle. I'm guessing the third one is an offset, or the Z value. The fourth and the fifth look to be like an index into what shape it is, and the sixth one, no idea. So we can take these and expand it, and we can regenerate every bit of every level. But there's nothing much we can do in terms of visual output showing us that we're doing something right. So let's skip ahead to the shapes. Shapes are things that we should be able to see. And going quickly, we have 0, 8 at the top. We have 8 entries with an offset and an index, and a bit. I don't know why that bit is set, but it is. Let's just skip that. And looking at this, I'm guessing that we're basically ending up at the end of the file if we do the same trick with the other file. Yep, that's the end of the file, except we're off by 8 bytes. No clue why we're off by 8 bytes, but I guess we are. We'll just ignore that we're 8 bytes short, because every entry is 8 bytes short, and we'll just assume they run to the end. Looking at the entry, we have this bit of data, and this looks like a header. All the way up to the end of 67, that looks like a header with a whole bunch of entries. And the entries look to end about here. So what's in the header? Probably width and height. So we have something that is 100 and something high, and 16 wide or 7 wide, depending on which pair we pick. Looking at the data, we have 68 entries. So I'm guessing it's the first one. 68 high, 10 wide, that should be a thing. We have these values. And looking at it in detail, these are run length encoding. Well, dang, we just did that. So the first one says we skip 7 pixels, and then we copy 2 values, and then we skip 7 more. That's 16. Second one, skip 5, copy 6, skip 5, 16. Skip 3, put 10, skip 3, 16. Now if we draw that out, it starts to look like this. Now that looks dang much like an isometric kind of graphic. Okay, so let's take this, put it in code, render things. And now my very own code is showing this. That looks hopeful. But we have this, and we have the stuff for loading a level. So if we take all that, put it all together, and try to do as much as we can just see what actually is in the file, and if we made wrong assumptions. There might be a couple of wrong false positives, there may be some corrupted files, but let's see how far we get. So we just take this, take the extracting from FLX, take the rendering of data, take the rendering of shapes, the offsets, the X, Y, and Z values, mess around a bit until it looks nice, and then we get this. So, yeah, that works. That was reverse engineering a whole game. And of course, the people who made this didn't grow up. So when you render all the levels and look in the corner, you will find this. Wow. Ah well. So going beyond this, we can try to identify if there's any kind of common file formats in here. If there's zlib compressed data inside your file, maybe there's some data files inside other data files. Sometimes people put PNG files in a different kind of file. We try to identify offsets and size pairs or indexes into data. We find different files with the same format, the different data to see what the fields might actually represent. We just try to invalidate our own assumptions. We try to identify all the regions and find out how big files are different. And maybe somebody else solved something similar. You can do this from reverse engineering the executable. It's probably illegal wherever you are. I choose not to. I just don't like it. So thanks to Moritz Mertenkat and Gavin Pugh for reverse engineering Red Alert and Command & Conquer and getting me interested in this. Thanks to Origin, Jason Ely, and Eric Wilmar, and the entire Crusader team for making this awesome game that crashed on my computer and is the whole reason why I'm here talking about C++. And thanks to EchoSector and the people there doing the stuff that they do. They are the community for Crusader No Remorse that is still active to this day. So, any questions?